XOR construction. Now, I would like to preface this video by saying that I use a trie for my solution, and I basically make a reduction into a standard problem that can be solved using a trie. So I'm not going to go too much in depth to what that standard problem is and how to solve that standard problem, because I have a video in the future where I'm going to be going in depth about trie data structures, and I'll most likely cover that standard problem in that video. So with that being said, we can make this observation. Let's say let's just start by saying that for some input array A, let's just use 1, 6, 1, 4, 1. We first notice that if we know the first value of array B, then we can generate all of array B. And the reason being is just by the definition of array A. So for example, if the first value of array B in this case is equal to 0, then we can generate the next value by finding 0 XOR 1, which is 1, and the next one by 1 XOR 6, which is 7, 7 XOR 1, which is 6, 6 XOR 4, which is 2, and 2 XOR 1, which is 3. So just like that, we can generate some array B if we know the correct first value. Now, in this case, 0 is not the correct first value of B because n is equal to 6. So we want to have this be some sort of permutation of the value 0 to 5. So notice that if we change the starting value to, let's say, A, then obviously this value goes from 0 to A, but the process of generating this array B stays exactly the same. So all we're doing by changing this first value from 0 to A is that we're XORing every value in array B by A. So this is essentially 0 XOR A, 1 XOR A, 7 XOR A, 6 XOR A, 2 XOR A, and 3 XOR A. And no matter what value of A we can choose in here, this transformation is the same. So we can rephrase this problem into the following. We want to check all values of A from 0 to n-1 inclusive, such that if we take this initial array B and XOR every value in this by A, we want to ensure that the maximum value in here is n-1. So now the problem becomes, for any value of A, if we XOR all elements in this array by A, does the maximum in here exceed n-1? And this is a trie problem that can be solved in O of n multiplied by log n, which in this problem is about 18. So by using a trie, we can solve this problem in O of n 18. I'll do a quick run through as to how this trie works. So I'm going to build a trie with these set of numbers. And in the problem, you start from the largest bit to the smallest, so I start from bit 18. But because all the numbers in here are small, I'll just start from the largest bit in 7. So this is a root of our trie. This is bit 4, bit 2, bit 1. So this is the number 7 because the 3, 2, or it's more specifically 2, 1, 0, because this is layer 2, layer 1, and layer 0. Layer 2, 2 to the power 2 is set in number 7, so we go to the right, and the same is true for all of them. And the opposite is true for 0, because none of the bits are set, we just go to the left child every time until we hit the bottom of the trie. For 1, it's a similar thing, except we travel, once we get to this layer over here, because the 0th bit is set, we want to take the right edge down. For 6, bit 4 is set, so we go right. Bit 2 is set, so we go right. Bit 1 is not set, so we go left over here. And then for 2 and 3, it's like a similar line of logic. Go left, go right, and we go left. And then for 3, it's left, right, right. So for this array B, this is what our try would look like. Now, to actually determine whether some mask would make it so that the maximum value in our set is going to exceed n-1 or not, we can traverse down the try and check which branch to travel down on. More specifically, if the bit of a level that we're currently on is set in n-1, then it doesn't really matter. Then no matter what, at least as far as we would know at this point in time, we wouldn't know that, we don't know for sure that a value has exceeded n-1. So we can just continue traveling down the try to determine if it actually does exceed it. And we only have to check one branch of one of these children, because in the other child, because the bit would not be set in that other child, whereas that bit is set in n-1, no matter what happens below that other child, any element in that other child cannot exceed n-1, because the most significant bit of n-1 would be larger. And in the other case, where if the bit of a layer that we're currently on is not set in n, we need to make sure that there's only one possible child that we can travel to. And that child that we have to travel to has to also make it so that that bit is not set in all of these values. Because if there is at least one element in this try such that at that layer its bit is set and the bit in n-1 is not set, then that implies that that value is going to exceed n-1 because it's the most significant bit at that time. And so because of that logic, we want to return false and say that this value of a that covers this try is not the correct value of a that we're looking for, and we move on. Once we find this correct value of a, then we can just set a to be the first value of the B array. So B at 0 is equal to a, and then we can generate the rest of array B like earlier.